Hi, in this video we are going to talk about how the graphs of functions and derivative is related. So let's remember the definition of derivative. F is said to be differentiable at a point x equals a if this limit h goes to 0, f of a plus h minus f of a all over h exists. So in other words, this limit exists if we have the left and the right limit of the same expression when h goes to 0 from the left and when h goes to 0 from the right are equal numbers, which is actually a finite number. So there is a theorem: if f is differentiable at x equals a, then f of x is also continuous at x equals a. So the proof is actually, if we assume that f is differentiable at a point x equals a, then the limit f prime of a equals limit x goes to a, f of x minus f of a over x minus a exists. Then, if we write first limit of f of x minus f of a as x goes to a, and then this is still equal to limit x goes to a, x minus a times f of x minus f of a all over x minus a. So the limit of x minus a times the limit of the quotient here is going to be 0. Why? Because the limit of x minus a term when x goes to a will be a minus a, which is 0. And the other term is equal to, the other limit is equal to f prime of a. So this is equal to 0. What is equal to 0? Limit of f of x minus f of a as x goes to a is 0. So if we write this limit, and then if we take minus f of a to the right, we are going to have limit of f of x as x goes to a is equal to f of a. And this is exactly the definition of continuity at the point x equals a. So that means if the function is differentiable, then it's also continuous at the point. So here is one example here. Let's look at the graph of some function like f. So the graph of the function is drawn by purple color. So the question is, at which points is f not differentiable? So if you look at the graph here, at the point 1 there is a jump, so the function is not continuous at 1. At the point 3, the function has a hole on the graph, so it's not continuous at x equals 3. At 4, there is a vertical asymptote. So this is also where the function is not continuous. So at x equals 1, x equals 3, and x equals 4, and also x equals 6, which there is another vertical asymptote, the function is not differentiable because it's not continuous at all. Now, if you look at the points 8 and 9, at the point 8, the tangent line from the left is, let's say, it has positive 4 slope, and the tangent line from the right to the graph has negative 5 slope. So, well, it's clear that these two slopes from the left and right, slopes of tangent lines, are not equal. That means the limit at 8, the limit of f prime at 8 doesn't exist. So the function is not differentiable at 8. And then at 9, the graph, when you look at the graph and if you draw the tangent line there, the tangent line is going like, it's actually vertical tangent line. So the slope of vertical lines are actually infinity. So it's not a finite number. So we have like three types of actually points here. 1, 3, 4, 6 function isn't continuous, and therefore the function is not differentiable. At 8, we have a broken graph, so the left and right tangent lines will have different slopes, so the function will not be differentiable at such points, at broken graphs. And at 9, the tangent line, when you draw, looks like a vertical line which has infinity slope, which is not a finite number. So because of this, at 1, 3, 4, 6, at 8, which is a broken graph, at 9, the tangent line is vertical, which is negative, which is infinity slope, not a finite number. So at these points, the function is not differentiable. Another example. Now, the graph of a function f is given like this with the blue graph. And the question is, sketch a possible graph for f prime. So how do we start to sketch the graph of f prime? At first, we look at the graph, the blue graph. There are actually local maximums, local minimums, like at 2, 4, 7, 9. So 2 and 7 are local maximums, 4 and 9 local minimums. Well, when we draw the tangent lines at 2, 4, 7, 9, the tangent line will be horizontal. So what is the slope of a horizontal line? 0, right? So horizontal line has 0 slope, which means the derivative at 2, 4, 7, and 9 is equal to 0. So we start with these points. So we put a dot on the x-axis, 2, 4, 7, and 9. Why? Because on the x-axis, y prime is 0. So anything 0 for y prime must be on the x-axis. And then if you look at the points before 2, if we draw the tangent lines before 2, we will have tangent lines going upwards. So any line going upwards have positive slope. So positive slope means, positive tangent line slope means positive derivative. So we have to draw the graph of the part before 2 with some positive piece of graph. Like anything above the x-axis will have positive f prime. So we can draw anything like this one I have drawn here. And then between 2 and 4, if you draw a bunch of tangent lines, as you see, all of the tangent lines will be going downwards. So any line going downwards will have negative slope. So that means the derivative is negative between 2 and 4. So derivative negative between 2 and 4, we can just draw something on the negative part, which is actually below of the x-axis. And between 4 and 7, tangent lines have positive slopes. So derivative is positive between 4 and 7. So f prime is above the x-axis. Between 7 and 9, tangent lines are going downwards, so negative slope between 7 and 9. That means derivative negative between 7 and 9. So we draw a graph below the x-axis. After 9, tangent lines have positive slopes, so derivative is positive after 9. So we draw a piece of graph which is above the x-axis after 9. And this gives the derivative of actually f prime. So, and the derivative of f of x, the thing we have used here is the derivative of f at a point is the slope of the tangent line at that point. So if the tangent line goes upwards, then its slope is plus or positive. So f prime is positive. If the tangent line goes downwards, then its slope is negative. So f prime is negative. If the tangent line is horizontal, then its slope is 0. So f prime is 0. So and exactly as we have said, at x equals 2, 4, 7, 9, the tangent line is horizontal. So at these points, derivative is 0. So numbers before 2, numbers between 4 and 7, and numbers after 9, the tangent lines goes upward. So f prime is positive. And for the numbers between 2 and 4 and the numbers between 7 and 9, tangent lines are downwards. So they go downwards. So f prime is negative. Another example, let's say we have a graph like this. So we have a vertical asymptote at 0, two local minimums at -5 and 3, and the local maximum at -2. So if we look at the tangent lines at -5, at -2, and at 3, the tangent lines are horizontal. So at -5, at -2, and at 3, derivative is 0. So we put a dot on the x-axis because that's where derivative is 0. Above the x-axis, derivative is positive. Below the x-axis, here, derivative should be negative. Then, also, let's look at the vertical asymptote at 0. Now, if we approach to 0 from the left, as you see, the tangent lines will have negative slopes, but as it gets closer and closer to 0, the tangent lines are going to be vertical tangent lines, which will have infinity slope. But as you see, they go like negatively very large, negatively arbitrarily very large. And then if we approach to 0 from the right, the tangent lines are again negative because they are going downwards, but as we approach to zero more and more, they are getting more and more negatively large. So the limit of the derivative when we approach to zero from the left and right should be negatively very large. So this x equals zero is also a vertical asymptote for the derivative graph. And then for the numbers less than -5, the tangent lines are going down. So negative derivative, it's negative slope, so derivative negative. So we draw something on the negative side. So this is what happens before -5. Between -5 and 2, the function, the derivatives are positive because tangent lines are going up. They have positive slope. So derivative positive between -5 and -2. And then after -2, tangent lines are going downwards. So negative slopes, that means derivative is negative after -2. Between 0 and 3, as you see, the tangent lines are going downwards. So they have negative slopes. So derivative negative between 0 and 3. So we draw it like this. And after 3, the tangent lines are going to be going upwards. So positive slopes, that means derivative is positive. So we draw like this. Okay, so as you see, at -5, at -2, 3, tangent lines are horizontal, so f prime is 0 at these points. From the left and right of 0, the tangent line slopes get more and more negatively, arbitrarily large, so f prime goes to -infinity as x goes to 0 from both left and right. And as I've just explained, we have negative slopes when the tangent line is going downwards. We have positive slopes when the tangent line is going upwards. So derivative has a sign accordingly. And there is a last example here. Let's say we have a function like this given by the blue graph. So we have like one asymptote at x equals 3, another vertical asymptote at x equals 6. And so there are also a bunch of points like 1, 7, and 8 where there are local min and maximum points. At 1, 7, and 8, the tangent lines are horizontal. So derivative is 0 at these points. So we sketch them like 1, 7, 8. And let's look at 3 and 6. First, let's look at 3. From the left of 3, the tangent lines are going up. So they are positive, but they are getting more and more vertical. So f prime goes to plus infinity as x goes to -3. So what we have here is going to look like this from the left of 3. And from the right of 3, the tangent lines are going upwards. But when we get closer and closer to 3, they are going more and more vertical. So they will be also going to infinity. So from the left of 3 and the right of 3, f prime is very large, plus infinity. We show it like this. And when we look at 6, from the left of 6, the tangent lines are going upwards, so they are positive. But as you see, when we get closer and closer to 6, they are getting more and more positively large. So f prime goes to plus infinity as x goes to 6. And from the right of 6, though, we see that the tangent lines are going downwards from the right. So they are negative, but when we get closer and closer to 6, they are getting more and more negatively large. So at 6, the tangent line is the derivative will look like this. From the left, f prime goes to infinity. From the right, it goes to -infinity. So we draw it like this. Okay, now let's look at the function again. If the numbers are less than 1, the tangent lines are going down. So f prime negative before 1. So we draw it something below the x-axis. After 1, between 1 and 3, tangent lines are going upwards. So derivative is positive. Eventually they get positively very large also when we get close to 3. So we draw it like this. Between 3 and 6, the tangent lines start very positively very large, and then they go less positive, some finite positive. But then when we get closer to 6 from the left, they get again positively very large. So we draw it like this, coming from plus infinity, getting some positive numbers between 3 and 6, and then getting more and more positive, and then diverging to plus infinity when x goes to 6 from the left. From between 6 and 7, as you see, the slopes start like negatively very large, and then they get less negatives finitely, eventually get 0 at 7. So we draw it like this, coming from negative infinity, coming to 7. Between 7 and 8, tangent lines are, as you see, going up. So f prime is positive, so we draw it like this. Between 7 and 8, positive f prime above the x-axis. And after 8, tangent lines are going down, so f prime is negative. But then, as you see, there is a horizontal asymptote here at y equals minus 2. What happens to the slopes? They get like as x goes to infinity, the slopes get more and more horizontal, which means f prime goes to 0. So we have negative slopes, but when x gets very large, positively large, they get closer and closer to 0. So we draw it like this. Okay, so this is the end of the video.